Okay, so I've started recording. Welcome everyone to the second lecture of machine learning. So our goal today will be to finish up our discussion of last lecture and then introduce some new learning algorithms based on or building our information and our knowledge about machine learning. A little bit about announcements and signups. If you haven't yet, please take a look at the Relate website, which has a link to Piazza. Please sign up for both Relate and Piazza. Relate is going to be our course management system. That's where you're going to get all the information about the course, homework, all those things, schedule. Piazza, we're going to be using for a lot of the communication within the course. There's already a lot of information on there, so I suggest that you consider joining. I also strongly suggest that you use Illinois credentials. I think Relate might force this. Piazza might or might not, but we'll be checking to see that you have Illinois credentials or you have special permission if you don't within the week, so please do. If you haven't had a chance to take a look at the survey that we put up, we would like to learn a bit about who's taking the class to help us with design and figure out things that we're missing. So on the Relate website, there is a survey that you could take. Homework 0 apparently is still not working. Okay, so that's good feedback. I thought we had fixed it. We will fix it today. So Homework 0 will definitely be released today. So Homework 0 is not going to be part of your grade, but it's going to be just for you to get a sense of what the expectation in terms of material in this class is. Also, again, please take a look at the survey. Please fill it out. I'm going to be keeping an eye on the chat as we go along, so feel free to ask questions there. I will eventually find a better way to do this that involves maybe other ways of interaction. There is a survey. If you go to Relate, there should be a survey right on Relate. Maybe I'll just go ahead and email it to the whole group. Maybe that's easier. If you go to the Relate website, there's a link right on Relate to a survey. The survey is mostly asking sort of what background you have. Actually, a lot of you have already filled this out. I think about half of the class. What background you have, what you're hoping to learn from the class, things like that, which helps us a lot in design. In terms of material, so my target is to have slides posted on Piazza before class under resources. So you should be there before the class, and then annotated slides posted after class on Piazza as well. It'll eventually get on Relate. Sometimes there's a delay for various reasons, but you can always get the slides on Piazza even if you can't find it on the Relate website right away, and usually much quicker. The video media space, which is what this ends up linking to, has had I had trouble anyway on Wednesday. Hopefully it's the last time, but we'll see. What that means mostly would be that there might be some delay. So the last video took a day or so to get out. Homework 0, we have mentioned. The LaTeX template for both scribes and homework is under resources. So go to Piazza. I apologize. They should have said Piazza, not Relate. Piazza for both of these. That's my mistake. So if you go to Piazza resources, you should find scribe examples, homework templates, and both of those. On Piazza as well, you should have a link to where you can find information about lecture scribes. Only 4 credit students are asked to scribe for this class. We're trying, it's a little bit different from previous years. And also you don't get to pick when you're scribing, so we're doing a kind of random assignment. So take a look. We'll try to update as people add and drop the class. Let us know if you have issues with any of these things. In particular, for the scribes, they're through Google Forms, and that can be problematic. Through Google Sheets. We'll try to find other ways to get that information out. That avoids some of these issues. Okay. So do 5CH, I don't know how 5CH. Do 4 credit students have to scribe all lectures? No. You're assigned to a particular lecture and you just have to scribe the lecture that you're assigned to. Extra credit for 3 credit students is going to come from class participation. We're primarily going to use Piazza participation, and as the class goes along, normally I use in-class participation. I know that I'll be worse at this semester. So I think I'll primarily depend on Piazza. As we go along, as I learn more about you, I'll maybe learn a little bit more about how other ways that I can get a sense of participation, which is how extra credit works for this class. Okay, so today we're going to cover linear regression. I'm going to defer details. Maybe I'll add a quick note on Piazza on how extra credit is thought to work. But it's roughly participation. It's very vague. It's vague on purpose. Again, it's extra credit. So I think the actual grading is, we're going to make as clear as possible. Unfortunately, the extra credit will be somewhat vague. Okay, so interesting. Who can't see my slides? Sorry, if you can't see my slides, can someone, I should ask a different question. Okay, so it shows for some people, doesn't show for others. I'm trying this thing where I'm signing on from 2 computers so that I can more easily check and hopefully avoid some of the lag issues. I don't know how to fix this in real time. I know that some people can see and some people cannot. It may be reasonable to quit and rejoin. I apologize. I don't know how to fix that tech issue right now, because I haven't seen that before. It's possibly because of the way that I set up. I see. So apparently there's an option, I guess you can all read the chat, but there's an option at the top left that allows you to view shared content. So maybe you can try that to see if you can get in. Okay, so last lecture, we talked about k-nearest neighbor, which is an algorithm, if you like, our machine learning 101 algorithm. So again, the idea was take a bunch of data. So give you a bunch of points. These are all pluses, these are all minuses. And now I'm interested in classifying some new points that's here. And what I'm going to do is try to figure out what the nearest neighbors of these points are. So I'm going to compute all the distances between this point and all of the other points in the data sets. And based on the distances from this point to all the other points in the data set, I'm going to, okay. Apologize for this. Apparently there's a delay. There's a very serious delay on the screen. Okay, hold on one second. Let me attempt to fix this. So for some reason, it is not changing screen for everybody. I can see it on my end as well, so it's definitely a problem. Okay. Just 1 second. Let me attempt to figure out what's going on here. Apologize for, I guess, growing pains on tech issues. Okay, before I try to figure out these issues, I'm trying to figure out why I can't share screen appropriately. So I apologize. I'm trying to fix that first because that's a pretty major problem. Okay. One second, please. Okay, I'm going to try resharing and seeing if it fixes itself. Maybe I'll try sharing my entire screen. Okay, this seems to be working. So we'll try this for now, and then apologies for this. Hopefully this gets more streamlined as we go along. So hopefully everyone can see this. Okay, so far so good. Okay, so k-nearest neighbors. Again, the idea is I take my entire data set, so data set which is xi, yi. So this is my data set of n samples. From these n samples, I take all of my input points, and for predicting a new point, so prediction of a new point, f of x is equal to the label of a particular point where L is equal to arg min of the distance between x and xi. So I'll parse this very quickly. This is one of the things we talked about last time. So again, the idea was I'm going to compute the distance between all pairs of points and myself. So this gives me the set of all distances. From this distance, I'm going to figure out the distance the smallest. And I'm going to find out the example associated with the smallest distance. Let's call it L. And I'm going to look up the label of that closest example. So that label is YL. And that becomes my prediction for the new point. So that's the way k-nearest neighbors works. The X is the point you're looking to make a prediction about. So again, I have a data set xi, yi, and I'm trying to make a prediction about a new X. So X is the point I'm trying to make a prediction about. It's literally nearest neighbor. So I find the nearest neighbor and I use the label from the nearest neighbor. And that's what k-nearest neighbors tries to do. The next question was, where does k come in? So very quickly, and I want to make sure we move on from this because we have a lot to cover this lecture. So I will briefly go over this and I'll defer to office hours and office hours and looking at the video for, again, some of the details we covered last time. So the idea of k is instead of looking for just one nearest neighbor, I can look for more than one. In particular, I can look for up to k nearest neighbors. And if you remember, the idea was that I can average or look for majority vote over my k nearest neighbors, and that gives me a way to make more stable predictions. So when k equals 1, I get simple nearest neighbors. When k is bigger than 1 and I run a majority vote, I get a more stable algorithm often. And this is what is known as k nearest neighbors. Okay, so one of the things that we spent a lot of time on last time was talking about the pros and cons of k nearest neighbors. So the biggest pro is that it is easy to implement and it's easy to reason about. So again, if you know anything about nearest neighbors, a little bit about distances, then k nearest neighbors is somewhat obvious. The biggest con is that k nearest neighbors, one second. So the biggest con is that the k nearest neighbors needs to store all the data. So there was a question about going over a less abstract example of k nearest neighbors. I'd like to push that to office hours because I think we won't have time to do that today. So we'll go over, if in office hours, I think we're starting officially next week. I should have one on Monday. I'm happy to go over a real example of k nearest neighbors to flesh it out. Okay, so the biggest pro of k nearest neighbors, easy to implement, easy to reason about. biggest con is that the model is all the data. So as the data gets really big, then the size gets large, the prediction speed starts to suffer. And the reason the prediction speed starts to suffer is that now I need to search more and more neighbors. So this scales with the number of neighbors I need to capture, but also it scales with distance. And in fact, dimensionality. So the higher dimensional my data, suppose I'm doing, say, text data, using words as my features. So easily I can get to 100,000 or so. I'm doing something in, say, imaging or in computational biology, I can easily get to millions of features. So that becomes a problem in terms of both storage and also prediction speed. We also discussed last time that it's susceptible to noise and outliers. So particularly in high dimensions, you could have problems with noisy predictions. So a question for the class, and I'll just look into chat, is actually, and I'll also ask some of the questions that you guys are asking because some of these are quite good. So the question for now, though, is why does a prediction model need to store all the data? I'll look for answers from the group. So does a prediction model need to store all the data? Okay, so some people say yes, some people say no. There should be a way to do a vote. Okay, so it's a mix, though it looks like the no's are winning. Okay, so the short answer is no. And in particular, today we're going to go over an example of a prediction model that doesn't need to store the data. And it'll be good to contrast this with something like k-nearest neighbors that does need to store the data in order to make predictions. So remember, if you remember from last time, in k-nearest neighbors, the cost of quote unquote training is zero because it's just, there's no training process. The cost of prediction is high because I need to search over all of my data points in order to find the right prediction. There was another really good question. So the question was, what are some ways to improve the prediction time? Any thoughts on what can we do to improve the prediction time of KNN? Okay, so one really good one, there's an answer that says use a KD tree. Can someone tell me what a KD tree would be useful for? So maybe make that slightly less abstract. Okay, so yeah, so you can speed up nearest neighbors a ton if you do a bit of extra work. So if you like, you can call this the training of the k-nearest neighbor. Is you can do smarter ways of computing k-nearest neighbors that involve a bit of pre-computation, like using one of the a KD tree or related type of approach. You could also use sort of approximate k-nearest neighbors that can speed up some of the things that you can do for prediction. You can use smart hierarchical organization. So there's a bunch of sort of data-based data processing tricks that I think can make a big impact. There are also approximation tricks. I think dimensionary reduction is a great idea. So I see that we have experts in the class who've seen things like, we'll talk about this in excruciating detail at some point. But things like PCA are a great idea. So in some settings, it makes sense to take really high dimensional features, reduce the dimension of the features to something more manageable, and then use that for your prediction method. And one nice thing about that is you can go for something like 1,000,000, some like 1,000, or even less, and may not lose anything in prediction accuracy. We'll spend a lot of time on PCA in the future. So we'll talk about this more later. Great. Okay. So today we're going to talk about a method that doesn't require you to store all the data. And we're going to talk about linear regression, which is considered essentially the simplest learning method if you live in machine learning world. But if you're a statistician, it's the simplest statistical model. Depending on the world you live in, it's sort of the simplest of the class of models. So remember, as we've been describing so far, we're starting off with supervised machine learning. So remember, the goal in supervised machine learning is to be able to make predictions for inputs. So I give you inputs, we call these features or covariates, and my task is to find a label or response for this input. So the idea of a linear model is my response for an input is just going to be an inner product between my feature and some model parameter plus some bias term. And if you're not familiar, I should mention that W transpose X is equal to sum over dimensions W D X D. So I take the two vectors and I do an element-wise product for each element of the two vectors, which gives me a new vector output. And then I sum this up. So, and this is the inner product. So this whole thing is the definition of the inner product. So very quickly, so covariates, I mentioned covariates based on lingo. If you're in statistics, the X is often called covariates. In machine learning, X is often called features. In different departments and different fields of study, the inputs are called different things. So these are just different names that you'll see if you're, say, reading papers or looking at literature. Same thing for outputs, the Y. So it's sometimes called label, sometimes called response, sometimes called dependent variables in statistics, where X might be called independent variables. So depending on the sort of literature you're looking at, you'll see the same name for the same thing. Linear regression has been around forever. It's been reinvented a few times. So it's one of those sort of long-standing algorithms that I think keeps being repeated over and over. Okay, so we've now described a linear model. What the linear model seeks to do is it tries to explain the output. So it's going to predict an output based on the inner product between the input and some parameter W, and then add a B. And so this linear function, really this affine function, which is linear plus this additional bias, is what is used as a prediction. We talked about when we call models linear or nonlinear in the last lecture very briefly. So this is an example of what is typically considered a linear model. So it's a linear model because the function that we're using for prediction. So remember, this is the function f of x that we use for make predictions for a new example. This function has a linear form. In this case, an affine form, but we consider it linear. Okay. So now the task of learning is to find these parameters. So I need to find a W and a B based on my data sets. And the task is to find a good setting of W and B based on the data. Any thoughts on how, well, we'll talk a bit about how I might do this in 2 seconds. The prediction task is given a new X, potentially one I haven't seen before. I want to be able to apply this linear function and then make a sort of estimate of the output based on this input. And importantly, and we'll talk about this over and over as we talk about different problems, you need to define, for supervised machine learning problem, you typically need to define a loss function or an evaluation function. This is a function that tells you how well you're doing. So in general, this takes the form of a loss. So smaller is better. But you can easily convert from a loss to a gain. You can just do negative of the thing. So it's not a big deal whether it's increasing or decreasing to be better. That's more of a technical detail. For this class, in general, we'll use losses as the main way we measure performance. So we'll be looking for models that make the error small. So if you like, we're looking for an evaluation error, in this case, squared loss, that makes the gap between the prediction and the known Y small. Okay, so how is W different from X? So X is the inputs, W and B are the parameters. Does that answer your question? I feel like I just repeated. If you could ask the question again, the person just asked that. Why half? So half is useful. It will come up in 2 slides. It turns out to be very useful for sort of canceling stuff out when we try to work out the solution to this problem. Does W need to have the same number of parameters as X? In general, and yes, so W needs to be the same. W tilde right now, which is W with a little swiggle on top, needs to have the same dimensionality as X. Okay, and then the rest of this, and B is a number. So if you don't remember, so R is the reals, right? So this is minus infinity to infinity. I did that badly. Hold on, So just a bit of notation. So R is, just write this as the reals. And then R to the D is the D-dimensional vector of real values. Okay. So we go through based on an example. So the example is going to come from Old Faithful, which is a geyser in Yellowstone Park, which many of you might have seen, which is a park that has been erupting for the past 135 years. So it's been around a long time. It doesn't erupt continuously. It sort of goes off and on over time. So we'll go to real data in 2 seconds, but let's do a bit of hypothetical. So what happens if, remember, I have to make our life easy, I'll talk about a very simple case where X is one-dimensional, right? So suppose this is X and this is Y. Okay, so suppose I'm in a setting, and our general goal is to learn a model. So the goal is that I'm going to give you a bunch of data, X, Y, and so I give you a bunch of data, this points of my data, and I want to learn this linear function. This is f of X. So that if I give you a new X, I can predict Y. So what happens if all of the X's coincide? So to be concrete, suppose have all the X's lined up. What is the linear model that corresponds to all the X's coinciding? You can work it out officially, but it's also easier just to, okay, so one answer is straight up with all the W's being 0. So remember, so maybe to remind you of some intuition. So W corresponds to the slope, and B is going to be offset away from the slope. You remember your sort of algebra and sort of geometry, so how we define lines. Okay, so I could allow a straight up line, but that causes a problem. Does anyone know what problem will be caused if I use a sort of straight up line, up down line? What slope will I have if I have a straight up down? Okay, so slope is undefined, W needs to be infinity. It's not a well-defined function, and it's not a function we'd want to use for prediction. So the other solution, and the solution that we're going to assume that you'll end up finding, is this. And for this one, okay, so someone has it. So for this kind of line, this is our f of X. So for this line, as you've described already, the prediction, f of X is equal to Y, is just going to be the average of all the points, which is equal to the value of B that minimizes the squared error from all of the Y's. This is an equation that comes up over and over again. That's good to remember if you don't already know it. But the average is the solution of a sort of least squares type problem. So again, B is a parameter I'm interested in because we're just fitting with all the same X's. The X doesn't matter, so that goes away. So we're just interested in finding a good value for B. And if I work out what this good value for B is, I can easily show that the optimizing B is equal to the average of all the YI's. Okay, so here's some real data. So on the x-axis is the duration of a certain eruption. Remember, this is Old Faithful. It erupts for a certain amount of time, and then there's a delay till the next eruption. And one of the remarkable things about the geyser is that these eruptions turn out to be actually quite structured. So the relationship between duration and delay seems to have quite a bit of structure. In particular, you might be able to eyeball that it looks sort of roughly linear with some wiggle around it. So there was a question about, would I get a lower loss if I use a large W? So I possibly could. I'd get in some trouble. I'll defer that discussion. It gets tricky to office hours. Okay. So if X is the same, you get the same thing every time, yes. So the solution now doesn't depend on X at all. Okay, so now in this, I've already answered this question, unfortunately, because I forgot my slides. But if I give you now this data, then you could imagine that a line like this is a good solution for this problem. So this is the line that goes pretty well through the data. So in general, this is in a bit of gory detail, but useful for us to understand what's going on. My task is to find a setting of W and B. So this is quote unquote the learning task, which is to find good parameter settings. So I want to find a value of W and B such that the average, so this is the averaging of the squared loss, which is the difference between my prediction, W transpose X plus B, and the data Y squared, that this difference is as small as possible. Okay, so I'm going to attempt to solve this problem. So let's talk through how we would solve a problem like this. So first, you might know this already, but it turns out that it's convenient to rewrite the problem from affine form to sort of linear form. So what can I do? I can take all of the x's, stack them together. So each example is stacked in a row. And then I add on a column of 1 to all my x's. At the same time, I take my w and I stack on w and b together. So I take the vector w, add on b. Just to check that we're all following, what's the size of this w matrix, a w vector? So I had a w size d, okay, d plus 1. Okay, so that's important. So this is an r d plus 1. By the way, this is always a good trick. This will show up in exams, show up in homework, things like that. Check dimensions. That's always a good way to check to see if you're doing things correctly. What is the size of x? So I take each x, which has to be the same size as w, so size d, stack them up and add 1. So now it's a matrix, so it has 2 dimensions. Okay, so the size is going to be, there are n x's. So this column is going to be of size n, and this part is d, and then there's additional 1. So this is r n by d plus 1. Okay, and then hopefully this is easy. What size is y? Okay, so the size of y is n. So what I have is y of size n, so there are n different y's for n examples, a stacked matrix x of size n by d plus 1, and then a stacked parameter vector, which is the original d-dimensional w with an additional stacked dimension of size 1 on top of it, which gives me a d plus 1 dimensional vector. Okay, so how can I use this? Once I have this matrix form, it turns out I can simplify the somewhat messy equation quite a bit. It's a good exercise to check this for yourself. This will again come up a lot. So we'll use this kind of matricizing of problems quite often. So what I've taken is I've taken a problem that was written as sort of a sum or an average, and I've rewritten it in terms of a norm using matrices instead of sort of numbers and vectors. So what happens, what's the size of x times w? So x w is going to give me some vector. Let's call this y hat. What is the size of y hat? This is somewhat basic. Okay, so this is, it's going to be a size n. So 2 ways to sanity check. One, you should figure out how to sort of quickly get sizes of matrix and vector products. Again, it's going to come up over and over again. X is of size n by d. W is of size, sorry, n by d plus 1, w is of size d plus 1, and I multiply the 2, the second dimension ends up canceling, so I end up with a vector of size n. What are the 2 2's and the, oh, okay, so I'll go over the definition of norms in 2 seconds, but it's also something, this will come up over and over again, so it's good to look up and understand. Okay, so the first thing, when I multiply matrices and vectors, you can figure out what the resulting sizes of those elements are. So D, just to recall, is the number of features. So I have an input of size D, which is a vector with D entries, each entry being some feature that I'm using for my predictive model. So D is the number of features in my model. If that's still confusing, can you clarify, I guess, what's confusing, or we can defer to Afsars for that. Okay, so the other way to check that things are reasonable is that distances, so this is a distance, right? So this is the L2 norm of, let's call it Z. So this is L2 norm squared. We talked about this last time, actually, when we were talking about K nearest neighbors. This is equal to, if I give you a L2 squared of Z, this is equal to Z transpose Z. It's supposed to be Z, not 2. So if I didn't have the squared, I'd need a square root around it in order to define the norm. So L2 squared norm or L2 squared distance here is just going to be, I compute the error between X, W, and Y. And I'm going to take the L2 norm squared of that error. And that's what I'm measuring, which turns out to be the exact same thing as squared loss averaged over the data. So X is of size N by D plus 1. N examples, the D plus 1 comes because we added this column of ones that ends up stacking an extra set of ones, which ends up making X times W bigger. Okay. Okay, so how do I solve this problem? Any thoughts if you've seen this before? How would I solve? So now I've written my problem. I originally had a somewhat messy vector problem. I've rewritten this as this matrix problem. How would I solve? Okay, so if you all remember, a good way to solve it, and particularly for OLS, this works really well. I'm going to take the derivative with respect to W of whatever quantity, this whole thing. And then I'm going to set this derivative to 0 and use that to work out. So this is meant to be derivative. So this is from basic calculus, or gradient, if you like. Yeah, that would also work. So in particular, I can work out the derivative. If you haven't done it in a while, this is good practice. Again, we're doing it here, but it's going to show up a million times all through the class. It will also, I think, help you see why the half is important. So when you take the derivative, one of the things that you'll see is that a 2 shows up in the derivative, which cancels with the half. So that goes away. So it takes away a factor of 2 that you'd have to take around. Why doesn't it matter that I'm dividing by 2 in terms of this optimization or this estimation problem? So I've arbitrarily added a half, like I'm multiplying the whole thing by a half. So I just said that it doesn't matter in terms of the solution. Why doesn't it matter in terms of the problem that I'm solving? Okay, exactly. So I've scaled the loss by something. Any scaling of the loss doesn't change it. So you can scale a loss function arbitrarily. This is also something good to know. It'll come up again by the way, I see some comments saying that we're going to get to 0. In general, you don't get 0 loss. So there'll still be some error even at the best setting of W. We'll talk about this more in a couple of seconds. But whatever the value is, scaling will always will not change the value of W that optimizes this problem. It's still a bit vague if you haven't seen this in a while. I'll cover it a little bit more. Actually, let me go ahead and work this out in a little bit more detail with the caveat that we may or may not finish our material today. But I'm learning that the online classes take a little bit longer because there are many more questions, which is great, actually. But it'll help me scale things as we go forward. So let me go ahead and work this out, actually. So if you haven't seen this before, x, w minus y, 2 squared half. I can always expand this out. I just showed you what the definition of the norm is. This is going to be xw minus y transpose xw minus y. If I work through that inner product, I'm going to get the following four terms. W transpose X transpose XW, the first term, minus, minus 2 Y transpose XW minus Y transpose Y. So that's just straight from working out this inner product. And then I'm going to take the derivative of this thing with respect to W, this whole mess. If you take the derivative, you end up with X transpose XW minus, I'm taking a bit of liberty with some of the details of the derivative, but I'll let you work out some of those details on your own. And then I'm going to have Y, there's an extra 2 here, sorry. So this 2 actually goes, there's a half and there's a 2, which is what cancels with the other things that makes it easier. And then you have a Y transpose X term. I'm going to set this to 0 and solve for W. And you can go ahead and work this out and you can get what the value of W should be. Okay. There's a question about 1 over n. So we've gone ahead and ignored 1 over n. The reason we can ignore 1 over n is the same exact reason that we added a half. So it's scaling the norm and the error, and it doesn't change the solution. How do we check whether the second derivative is a min or a max? That's a great question. I'm going to defer that question to 2 lectures from now when we talk about convex problems, where we'll go over this in a lot more detail. Or you can refer to your sort of old calculus. If you don't remember, you should, so essentially you can work out the second derivative, but it's actually a really good thing to check. That's an extremely important point. Okay, so we've worked out the derivative, set it to 0, and we get that the solution is this W. So the claim is that if I plug in this as my choice of W, this is the best choice of W that I can get for this problem. And so when it exists, I can write the solution as X transpose X inverse X transpose Y. Question for the class. I added this specific thing when it exists, which implies that this solution doesn't always exist. What might lead the solution not to exist? What might be a problem in terms of the solution existing? Okay, so the biggest thing is I'm inverting a matrix here. And if you remember from your linear algebra, matrix inverses can be problematic. And so I may not be able to compute that inverse if this X transpose X is not invertible. So if this inverse doesn't exist, then the solution written this way doesn't exist. And so you need to find another way to solve it. Any thoughts on what I can do if this inverse doesn't exist? So what might be a solution if I'm in a, okay, so there's not a pseudo inverse. That's a great option, and it's one of the options we'll take. There's another solution that's common. Does anyone know? The other solution is regularization. Okay, so let's go over these in some detail. So what do I do when it doesn't exist? By the way, just a quick note. In all of your homework and in tests, unless we tell you that the solution doesn't exist, you can just assume that this inverse actually exists, and you can just sort of assume that you can move forward. So if we are asking for a setting where it doesn't exist, we'll be very clear to tell you that it doesn't. Okay, so the first option is the pseudo inverse, as many have pointed out. So again, I'm going to replace the inverse with a pseudo inverse. You can do a little bit of extra algebra. If you look up what the definition of a pseudo inverse is, it just works out. It turns out it's actually quite nice because the solution is equivalent to just doing the pseudo inverse of X times Y. So this still satisfies the derivative condition, which is important, which is this whole thing where we said the derivative of dw of something is equal to 0. This is also satisfied by the pseudo inverse. And so I can easily show that this is also a valid solution for this problem. So it's still an optimal solution, even though X transpose X is not invertible. So that's nice. So that's one option. We'll go in later on, we'll try to build intuition about what the pseudo inverse is doing and sort of what's going on there. The other option that I saw mentioned is to use regularization. So this has a name because it's very common. It's also known as ridge regression. So I have my original loss function, what I was optimizing before, then I add an extra term. So this extra term is a scaled norm of W. And so if I work out the same exact sequence of optimization that I worked out before, but now with this extra lambda over 2 times W, what I get is that the solution is X transpose X plus lambda I inverse X transpose Y. Why does, it's a good question in the slides, but why does this version work? Why does ridge regression work when the original problem was not invertible? Does anyone remember? So why is this problem a good solution? Okay, so to avoid the layout I just mentioned, so this, as long as lambda is positive, this will always be invertible. So any lambda that's positive will lead to an invertible solution. We'll talk a lot in this class about how to pick lambda. Lambda is something known as a hyperparameter. These are parameters, this is A, parameter. So these are components in learning problems that are typically tuned in what is known as cross-validation. Again, we'll spend a lot of time in talking about this in later lectures. But it's quite common, and in fact, it's probably the most common solution to this least squares OLS problem is to add this regularization parameter. And what it does, we'll build on this some more, but the intuition is that it tries to penalize the size of W getting really big. And this is one of the ways that you can control the complexity of the function that you're fitting. And in practice, it allows you to actually get a sort of invertible problem. There's a question about how do you pick between the first solution and the second. That's a really good question. I don't know of a nice formal, I know that in practice, almost all solutions use the regularization solution. We will talk a little bit about the properties that they capture in future lectures, which will maybe hopefully give you a bit of intuition about when you might want one versus the other. They do end up with different solutions. So picking lambda and making it invertible gives you a different solution than trying to use the pseudo inverse. That's an interesting question though. In practice, the lambda regularization solution, which is the ridge regression, sorry, that's what I mean by regularization solution. So this is solution if I add a regularizer, which is adding this extra term, which is called a regularizer. As we talked about a few slides ago. Okay, so as I said, this additional term is called a regularization. We'll spend some time talking about how it affects this estimation problem. It turns out to affect both the computation, as we've already seen, it makes this problem invertible, and it also affects the statistics. So it actually will affect sort of the statistical properties of the solution we end up fitting, which is going to be useful for sort of downstream analysis when we talk about generalization and other properties of learned models. Okay, so let's take a half step back and we're going to try and do some more sort of justification for why sort of least squares and least squares lines are good solutions. In this class, we're going to cover 3 justifications or interpretations. These are the main ones I know of. It's possible that there are others. Again, ridge regression shows up all the time. It's being reinvented in several fields over and over again, so there are possibly other solutions. There's a question, is ridge regression similar to lasso? The answer is it's similar in that they're both regularization methods. Their details, lasso uses an L1 norm instead of the L2 norm, so it ends up having quite different properties. We don't cover lasso in detail in this class, but I'm happy to cover it on offline in office hours. Okay, so first let's go with geometry, and let's try to build some geometric intuition about what ridge regression is doing. So suppose I take my data. So remember we had this x of size n by d plus 1, n d plus 1, okay? And now I'm going to look at every column. So I'm going to look at the sort of the space of columns of this x. So this is every dimension. So think of this as every z is a different vector. And I can look at the span of all these vectors, which is, if I give you a bunch of z's, I can look for a plane. This is, unfortunately, we can't draw in more than 2 dimensions. So this is d plus 1. Can someone answer why it's d plus 1 and not d? It's been asked a few times. Why is the size of big X d plus 1 and not d? Okay, so we're adding this extra term, a stack of 1s. So there's an extra b on the weight, and we're adding this extra bias term. So the full dimensionality is the original X, which is size d, plus this extra term for bias. So it ends up with d plus 1. So hopefully that's clear if you're asking that question. Okay, so I'm going to look at my data. I'm going to look at the span of my data, which is if you remember from your linear algebra, the span of sort of a set of vectors is sort of all possible vectors that can be constructed by combining your initial sets. So if you like, if I have a set of vectors and they all live on a plane, then the span of my vectors is the plane that where all of the vectors lie on. So if I look at the span of all of my data, and I also look at y, which is my error, my sort of prediction vector. So this is the target vector, and this is the span of data. So I'm going to do the following thing. I'm going to look for the orthogonal projection of my data onto the span of my, I'm going to look for the orthogonal projection of my target, of my label, onto the span of my data. And if I do this, so if you remember, again, a bit of linear algebra, we won't use this particular detail a ton. I'm going over this if you have some good linear algebra intuition and you think geometrically. Hopefully this is helpful for you. If not, we'll try to follow this section. And again, we're always happy to cover in a lot more detail. Okay, so I take my output y. I try to project it from the vector down to the span of my data. If I make this projection, you can show a couple of things, which are, I think, kind of cute and clever. So one, you can show that the orthogonal projection is going to be given by xw, which is nice, which means that xw is special. It's kind of the special vector that happens to be the orthogonal projection of y onto the span of the data. And if you remember your linear algebra, the orthogonal projection is the minimum error projection of a vector onto a vector space. So if I have a plane and I project the vector to a plane, the minimum error projection onto a plane is the orthogonal projection. So what this is saying is that the least square solution is actually sort of special as a projection of the label onto the data, because it's the minimum error projection. So it's this orthogonal projection of the label onto the data. So this becomes your error, which is y minus xw. And the special projection is known as the sort of orthogonal projection. So that's one intuition. Geometric interpretation is that you're projecting your output onto the span of your data, and the best projection you can find is the OLS solution. So this least square solution. So that's one intuition. And there are many ways to show this. The easiest way is to just roughly work it out. Projection is orthogonal if the inner product of the inner products are 0. So this error is equal to xw minus y, and this span of the vector space is given by x transpose. And if I do the inner product of the two, I get 0, which is the definition of the gradient condition that we started off with. So this is one way to check that this intuition is true. So that's nice. That's one reason why we like ordinary least squares or least square solutions. Here's a completely different intuition that comes from modeling. So suppose I think that I want to choose a model for my observed data. And my choice of model is that underlying my data is a linear model plus Gaussian error. So in particular, there's a visualization of this example. I have a relationship between X and Y. And I think that at every point, Y is equal to W transpose X plus some error, where error is Gaussian, 0 sigma squared. So if this is my model for how my predictions come about, then I can actually work out what W has to be a good fit for this model. And conveniently, this will actually work out to be the least square solution once again. So to recap, again, I have a probabilistic model. I'm going to now create a model for my data that says my observed data, Y, is equal to is given by a linear model with Gaussian error. So this is given by a model that looks like this, Gaussian linear model, additive error. And I can work out what this CDF has to be. So the conditional distribution function of the Gaussian. I should mention one, hopefully this is familiar to most of you. If it is not, it's good to have a good refresher or look at homework 0 to refresh expectations for sort of material. Hopefully you're familiar with Gaussian distributions. If not, again, we should chat offline to get up to speed. We're going to use simple distribution families quite a few times as we go through the class. Okay, so this is the PDF of a Gaussian. You might be familiar with it. Does anyone remember the sort of 101, the simplest method, the most common method we use to find parameters of a probabilistic model? Does anyone remember the name of the sort of procedure that is most often used to find parameters of a probabilistic model? Maximum likelihood, thank you. So MLE is short for maximum likelihood estimate. So that's exactly what we're going to do. So we've posited a model. We said that our data is given by a linear model with Gaussian error. We're going to find the maximum likelihood estimate of this model. So this is going to be the argmax of the data likelihood. This is coming from our model. This is a model, right? We said that this is what is generating our data. And so this leads us, again, I'll leave you to work through some of these details. Hopefully it's sort of obvious. Actually, I should ask, let me see if I have it here. I do not. Okay. How do I get from the left to the right-hand side? There's a critical step that allows me to go from left to right. Okay, so this is important for when you're looking at this later. I use the log of P of Y given X. And why is the log okay? Thanks for that answer. I'm avoiding names because I don't want to say names wrong, but maybe I should go ahead and say names anyway. So log, exactly. So log does a couple of things. One, log is a monotonic function, so it increases, which means that if I'm maximizing something, the solution of the log is the same as the solution of the original thing. So that's good because it doesn't change the optimum. Two, log plays well with products, which is very nice. So log of a product is a sum. So it turns something that was a product into something that's a sum, which simplifies a lot of computation. Three, log plays really conveniently with exponential. So if I have an exponential term, log with exponential, exponential. Log cancels with exponential, and that goes away. And in particular, I think correctly pointed out by in the chat that products of small numbers can result in computational issues. And luckily, log is much better behaved. So computationally, it makes a lot of sense. Algorithmically, it turns out to make a lot of sense. It just makes your life a lot easier. Other question, why do we have argmax and argmin? Can anyone tell me why we're able to switch from argmax to argmin? So there's a reason when we work through, exactly. So if you see here, we have a minus. So it's going to be an argmax of negative something. So maximum of negative something is the same as minimum. So that's how we switch from maximum to minimum. Good question. The next question was, why can we assume additive Gaussian errors? That's a great question. So we'll talk about this more as we go through the class. the choice of Gaussian additive errors is a modeling choice. Modeling choices are assumptions. If you like, this is a quote that is attributed to George Box, but I don't know if I think it's not clear if he actually said it, but the quote is that all models are wrong, some are useful. So if you like, as we're making models, we typically make assumptions, and a common modeling assumption, often partially checkable, is to see whether the errors look like they're Gaussian type errors. And a common modeling real world assumption is to use Gaussian errors as a model for what the deviation looks like. It turns out to work pretty well in practice. I will defer it offline for some motivations and reasons why that's a good idea. It's actually quite fascinating. But it's a standard modeling assumption to sort of have Gaussian errors. Okay, so we've gone through two motivations. We started with geometry. We said that the least square solution is this ideal suborthogonal projection from my output to the span of my inputs. We had a probabilistic modeling motivation. We said, suppose we were modeling using a linear model with Gaussian errors, then what you get out is the least squares problem, which is a nice fit. And now we're going to go directly to the loss function. So now we're interested in optimizing a problem where we're using squared loss as our loss. This is how we started, but again, I think it's useful because in machine learning, this is typically how we set up problems. We set up a model, we set up a loss function, and then we sort of work through an optimization procedure. So in this setting, our model is the linear model. Our loss function is the squared loss. And if you just work through it, that exactly gives you the optimization problem that we're interested in solving. This will come up a ton. This, again, as I said, I'm repeating some, but to highlight, this is in some ways the basis of modern supervised machine learning. It's an idea called empirical risk minimization. We'll spend quite a few lectures on different aspects of it. Some things to mention now, very briefly. Empirical comes from the fact that we're using averages from data as a way to measure the performance. Risk is because we're using a loss function. So risk is like, how much does it cost to make a mistake, which is what the loss is meant to measure. And then minimization is the idea that we're trying to minimize risk. And so in most of the algorithms that we come up with, we'll often try to set them up as an ERM problem, empirical risk minimization problem, where we'll turn them into some kind of empirical risk function, so an average of some kind of loss, and we'll look to minimize some parameter over this average of some kind of loss. So this would be the standard setup for most of the algorithms we'll talk about in this class. Okay, so let's talk a bit about how to solve this in real settings. So conveniently, X transpose, the closed form solutions, the solutions that we wrote in terms of vector and matrix operations are in nice closed form. But if you look at how these problems are actually solved, no library actually, well, internally to the libraries, most libraries use some kind of iterative solver. In particular, since the loss function is convex, this came up in chat, I'll defer why or the definition to 2 lectures. We'll spend a whole lecture on convexity, so I'll defer for now. But if you already know it, it turns out that convex functions are the kinds of functions where iterative methods work really well and give you good solutions. And we'll talk about why in a couple of lectures. But the main point of this slide is to mention that in practice, the way these types of problems are typically solved is not by closed form. It's typically by some kind of iterative method. And in fact, most of the machine learning problems we'll come up with, including when we talk about deep learning models, probabilistic models like variational autoencoders, things like that, will mostly use iterative solvers as ways to solve these problems. Okay. Sometimes we want to fit a model where linear doesn't seem good enough. So if I just fit a linear line, it gets most of the data, but this is not a great linear line, by the way. But anyways, suppose this was a better linear line, but there's still some deviations. I might think that these deviations are meaningful. What can I do? Does anyone know a simple trick to still keep the problem sort of a similar complexity and similar difficulty, but actually maybe get a bit of nonlinearity? Is anyone aware of sort of what can you imagine might be a reasonable solution? Okay, so I saw polynomials, I saw kernels. We'll talk about kernels a little bit more later. I think polynomials, we'll just go with a polynomial. So in particular, what you can do is you can get simple nonlinear functions by doing a feature transformation. We'll talk about this more later, but I take my xi, which is my data. I'm going to replace my xi with a feature transformation of some kind. So for instance, I can define x equals to xi and maybe xi squared. And if you like, I can add a cubic, because why not? Right, and stack these together. And this is my new sort of stacked representation. And I can now solve a linear problem with this extended x, which is like much, much bigger. And this is a common way to allow you to fit more complex function classes while still keeping things linear. So in terms of the overall semantics, it still looks like a linear problem. But in terms of the actual sort of representation on the data, you've taken your original features and you've applied some nonlinear transformation to it. I see piecewise linear. That's also a good solution. We won't talk about that very much in this class, but I think that's also a good approach. We'll mostly use like polynomial feature transformations and kernels as ways to fit nonlinear functions. But good idea there. Okay, so let's switch gears a bit. So far, we've been talking about a least squares problem where the output is a real number. So this is good for regression problems where what we're interested in is like outputting some value that is somewhere between minus infinity and infinity. However, we're often interested in classification problems, as we talked about last time, where what we want to predict is a number that's either +1 or -1. And so how might we turn a least squares regression into a classification problem? Does anyone want to guess? Yeah, exactly. So, so we're going to do exactly what's in the chat. We're going to learn the least squares problem like before, and then we're going to threshold the output. So let's go through some of this detail. So in particular, the strategy is, as we just discussed, we're going to find a parameter that minimizes the least squares loss, just like before. And then we're going to make a prediction as a sign of the output. So it's good to think about what this is doing. We'll spend some more time on this in a little while. One, it's good to mention fun identity. So if y is binary, so it's either -1 or 1, and those are the only two values that it can take, and I can rewrite the least squares loss as another kind of least squares loss, but one that has y times the prediction. I mention this because this ends up coming up all the time. It's a good way to solve binary classification problems. So in particular, most of the losses that we'll talk about, including logistic loss in the next lecture and many other losses in the future, take the form of the output times the prediction and some function of those as the way that they make the prediction. So this style of writing losses will come up quite a bit. In particular, if I make this axis y times y hat, and I make this axis loss, then I can draw out what the loss looks like. And the loss looks like a quadratic function, which is shifted on the x-axis a little bit by 1. So it's a quadratic function centered at 1, right? So what is it saying? It's saying that if my y and y hat have the same sign, then I'm in a good place. I'm going to be at 1. If y and y hat have different signs, then I pay a quadratic penalty depending on how far, what the magnitude of y hat is. So if the magnitude of y hat is large, if y hat is big, then I pay this big quadratic penalty, either positive or negative. This is in contrast to, and importantly, actually, I should mention, this is true both if you're correct and if you're wrong. So for instance, if y and y hat have the same sign, so if suppose sine of y hat is equal to y, so suppose they're both positive, but y hat is large, then you still pay a large error. So this will come up a lot more. The important piece of this is that squared error gives you a loss whether you're very, very correct or whether you're wrong. So both very correct and very wrong lead to a penalty. There's a question about what the bolded one means. That's an indicator function. So indicator function is 1 if true, and 0, or well, you can do 0 or -1, but in this case we're using 0. So whatever quantity is inside, it's 1 if true and 0 otherwise. The question is, why should the magnitude affect the loss? That's a great question. So the point is, ideally the magnitude should not affect the loss. And in fact, some of what we'll talk about, sorry, let me say this better. So the nature of loss functions that we typically use is that the magnitude ends up affecting the loss. One bad property additionally of squared loss is that actually positive magnitudes still affect the loss. So being correct, but being, if you like, too correct, so making a large prediction in the right sign actually still gives you a high loss. Whereas in the future lectures, we'll talk about other kinds of loss functions that have the property that sort of large good predictions tend not to lead to high penalties. So we'll talk about this in future lectures. For now, the takeaway that I'm hoping you take from this is we've chosen a loss function, right? So we just said, let's take the least squares loss function, let's apply it for classification anyway, right? So we didn't say we're going to design something special. We took a problem that was designed for regression, where we're looking to predict the real value things, and said, let's just use it for +1, -1, and let's see what happens. And what I'm trying to describe is the sort of the resulting properties of that algorithm. So one important resulting property is that it penalizes both big positive and big negative sign predictions. It's also worth highlighting the classification error loss. This is sometimes called the 0-1 loss. So this is this black curve over here. So again, it's this indicator function. If you're correct, it gives you 0 loss. So you don't pay anything for being correct. If you're wrong, you pay a cost of 1. So every mistake you make, no matter how bad the mistake is, you pay a cost of 1. Whenever you're correct, no matter what you predict, you pay a cost of 1. So if I plot the loss versus y times y hat, I get out this curve. And we'll plot these kinds of curves for lots of different kinds of prediction functions to see what the different properties are. So yes, for prediction, we're only interested in the sign. It turns out that, in fact, I'll mention this now. So it turns out that even though we're only interested in classification, using this kind of strategy actually works pretty well in practice. It's somewhat surprising, but it actually worked quite well. So this maybe handles or answers this generalization question to some extent. Yes and no, I guess, is the short answer. It's a little bit detailed and nuanced. I think the takeaway that I'd like to get across is, at least in terms of intuition, it seems to be a bit off. In practice, it works well, actually. The other thing I want to mention, which is super important, is that even though we wrote down the actual thing we want, which is this indicator of mistake, this exact loss, optimizing exact losses like this is hard, and hard in the computational sense, meaning it takes exponential time to find a good solution. Can anyone tell me, do you have any intuition about why this might be a hard problem? So computationally hard. Hopefully that's somewhat legible. So when I say computationally hard, I mean in a sort of theoretical order-wise hardness, like computational hardness, theoretical type statement, as opposed to just a purely computational statement. So the first is yes. So it doesn't have any good derivatives. It's a sign function. It actually ends up being a combinatorial problem. So it's a combinatorial problem that doesn't have sort of good derivative behavior. And so you can essentially, if you know a bit of theory, you can show that you can come up with instances that you can't solve without taking exponential time. So this is how you prove sort of hardness of certain kinds of problems. So in fact, even though what we want is to minimize number of errors, in practice, what we always do is minimize some other function and then measure the errors of those functions, something like squared loss. So we are out of time. I'm going to skip all the way. Oh, we're also done, which is great. So look at the quiz offline to summarize some of what we learned in the course. So we mostly covered least squares. We talked about regularization for least squares using ridge regression. And we talked about maximum likelihood as a way for solving these kinds of least squares problems. And then we also talked about loss functions and empirical risk minimization. And least squares classification as just taking the least squares problem, which is meant for regression, and then applying it for classification anyway. Here's some notation. I'll try to update this as we go along. Some feedback from previous years is sometimes people get lost in the notation. I'm going to hang around. I'm going to stop recording, but I'm going to hang around if anyone has questions, and I'll try to answer those for the next 15 minutes or so. So we'll stop recording. Feel free to leave, and just try to answer questions as we go.